Hello, everyone. My name is CharlieDrake, and welcome to my Master's of Science in Geographic Information Sciences Technology capstone presentation. Today, I'll be focusing upon and discussing Landsat-based classification of vegetation and snow around Hoh Glacier, located in Olympic National Park between the years 1987 and 2022. Located in the northwest region of Washington State, the Olympic Peninsula possesses both the Olympic National Park and the Olympic Mountains upon it. The region, according to the United Nations Educational, Scientific, and Cultural Organization, is renowned for possessing a variety of ecosystems, including but not limited to 100 kilometers of undeveloped coastlines, old growth temperate rainforests, high alpine meadows, and mountains mantled by glaciers, all within a temperate, mild coastal climate. The climate of the peninsula actually contributes to its diverse ecosystems, regions, and capacity to possess glaciers. The mild temperatures exist year-round within the region due to the nearby Pacific Ocean, and regions along the western shores up until the Hoh rainforest rarely dip below freezing, and temperatures atop the tallest peak, Mount Olympus, rarely dip below 0 degrees Fahrenheit during the winter. The region also exists at the lowest latitude where glaciers can form below 2,000 and 1,000 meters. During the autumn, winter, and spring seasons, the western regions of the peninsula experience copious amounts of rainfall. And along the precipitation gradient ending upon Mount Olympus, where Mount Olympus receives 260 inches of yearly precipitation, enabling glaciers to form upon it. However, Mount Olympus itself creates a rain shadow, so the land northeast of it actually receives very little rain in comparison, only 30 inches, and actually possesses fire-adapted foliage. To contrast this, during the summer season, the western shores of the peninsula actually only receive 3 inches of rain during that season. The region's geographic isolation, variety of climates, and varying elevations produce a high quantity of endemism and biodiversity. For example, the peninsula itself only has approximately 9% of the state's area, yet is host to over 25% of the state's rare plant species, and rivers such as the Hoh, Solduck, and Keats are important habitats for keystone salmon, trout, and steelhead species. And the Hoh River itself is considered a stronghold for these species by the Western Rivers Conservancy. Located about 35 miles inland from the western coast lies Mount Olympus, a peak resting at 7,980 feet, or 2,432 meters above sea level. Alpine glaciers upon Mount Olympus flow into the Hoh and Keats rivers, and actually possess approximately 80% of the glacial ice within the Olympic Mountains. The Hoh River is fed by glaciers such as the Hoh, Blue, and White, and they actually contribute approximately 15% of the total stream flow between the months of May and September. And during a critical time when rainfall is particularly scarce, between August and September, the glaciers themselves provide approximately 18 to 30% of the total stream flow of the Hoh River alone. So, the goals of this project were to classify the terrain immediately surrounding the Hoh Glacier utilizing NDVI and NDSI collected at 5-year intervals between the years 1987 and 2022. And Landsat imagery used to perform these analyses originates from the United States Geological Survey's Earth Explorer repository, and was collected in between August 15th and September 30th in order to minimize both snow and cloud cover in the region. One of the methodologies that I utilized was known as NDVI, or Normalized Difference in Vegetation Index. It is used to quantify and visualize the health of vegetation. It is calculated by dividing the difference of the near-red infrared band and the red band and dividing it by the sum of those bands. And in order to classify it, cell values of 0.1 or less are considered to be barren ground, including rocks and snow. Values in between 0.1 and 0.5 are considered to be grasslands or possess sparse vegetation, and values beyond 0.5 are considered to possess dense vegetation. The three maps you see on the slideshow are a false color Landsat image of Hope Glacier in 1987, an unclassified NDVI image of Hope Glacier, and the same image after classification, where barren ground is classified by yellow, sparse by orange, and dense by red. And each of these is clipped to the study area surrounding Hope Glacier, which was created via watershed. The other methodology that I implemented for this study was NDSI. NDSI, or Normalized Difference in Snow Index, is used to quantify and approximate the probability of snow existing upon the ground. And it's useful for differentiating snow from surrounding terrain, such as vegetation and rocks. It is classified by taking the difference of the green band and the shortwave infrared band and dividing it by the sum of those values. And cell values exceeding 0 are considered to have some snow present, whereas values below that are considered to have no snow. Like the NDVI slide prior to this one, this slide depicts a false color Landsat image, an unclassified NDSI image, and the same image post-classification, where cells that are believed to have snow have a whitish gray color, whereas cells that do not have snow upon them have a gray color. So, from 35 years of NDVI classification, what was found? On average, barren ground encompassed approximately 81% of the study area. Sparse vegetation encompassed approximately 19%, and 0.22% of the study area was considered to be classified as possessing dense vegetation. For the year 1987, these barren ground encompassed approximately 84% of the terrain, sparse vegetation, 16%, and dense cover encompassed 0.01% of the land of the study area. However, ending in 2022, these values were 78.6, approximately 21, and 0.64 respectively. As a whole, across the 35 years, this reflects a 5.25% loss in total barren ground, but an increase of sparse and dense vegetation by 4.62% and 0.63%. And across the 35-year time series, at 5-year intervals, we actually see that barren ground lost approximately 0.62% of land cover per 5-year interval, according to the trend line. But sparse and dense vegetation increased by 0.5 and 0.1% respectively during each interval. When it comes to NDSI, on average, the study area was classified as possessing approximately 70% of cells likely possessing snow and 30% of the terrain lacking it. In 1987, 82% of the terrain was classified as possessing snow and 18% of it lacked it. In 2022, these values were 55 and 45 respectively. And because these variables have an inverse relationship with one another, the total percent change was 27.03 for each variable, where over the course of 35 years, snow cells lost 27% and lack of snow gained 27%. Which is about 3.35% average per 5-year interval. So, over the course of 35 years, we've seen a shift in land classification with barren terrain, which includes barren terrain of NDVI, which encompasses barren rock and snow cover, and a loss in snow-covered terrain from NDSI. And we have to ask, why is this occurring? In 1980, there were approximately 266 glaciers spread across the Olympic Range. However, in the present day, only 184 of them remain, and only 4 of those exceed an area of 1 kilometer. Glaciers are sensitive indicators of anthropogenic climate change, and by 2070, glaciers within the Olympic Range are largely expected to disappear. In the present day, summer months have increased by half a degree Fahrenheit during the summer across the Pacific Northwest. And winter months have actually increased in temperature by 1.26 degrees Fahrenheit. In the 2020s, it's estimated by the Washington Climate Change Impacts Assessment that temperatures will increase across the Pacific Northwest by 1 to 3.4 degrees Fahrenheit. By 2040, this temperature change will be from 1.6 to 5.2 degrees Fahrenheit. And by 2080, these temperatures are expected to be in between 2.88 and 9.72 degrees Fahrenheit. Climate change will also create wetter summers and drier summers. Within the Olympic Peninsula, across the Pacific Northwest, in the 2040s, an estimated 3.3% increase in precipitation is projected to occur. And in the 2080s, this value is 7.6. During the summer months, less precipitation is projected to occur at 8.5 for 2040 and 12.8 for 2080. As a whole, the glaciers of the Olympic Range are particularly vulnerable to increasing global temperatures due to them existing in a mild, low elevation and latitude climate that is coastal. As temperatures increase, mild winters will get warmer, causing precipitation to fall as rain instead of snow, resulting in glaciers being unable to accumulate mass. And the snow line for every 1 degree in increase in Fahrenheit is set to increase by or decrease by 300 feet. And due to warmer winters or due to warmer summers, glaciers will waste faster during those times when there is a lack of rain as well as higher temperatures. So, glaciers in the present day actually play a key role in providing rivers, like the Hoh, with cool fresh water. And that cool fresh water is vital for keystone fish species, such as salmon, to thrive. Without the influence and meltwater of glaciers, river flow will actually decrease and the water will get warmer. High water temperatures actually act as a barrier for salmon and further fragment water habitats. When water temperatures reach 59 degrees Fahrenheit, salmon are weakened, are subject to increased predation, and are outcompeted by their rivals. And when temperatures exceed approximately 70 degrees, adult salmon become severely weakened, and adult salmon, as well as their fry, are increasingly subject to fish kills. During the winter months, when precipitation is more likely to fall as rain instead of snow due to warmer temperatures, the survival of reds, a spawning nest created by fish, is impacted, as eggs can be crushed by gravel due to increased water flow, suffocated by sediments, or fry being flushed down from ideal habitats. As a keystone species, the impacts occurring to salmon will radiate up the food web, stressing organisms which are normally enriched by their presence. Even forests are vulnerable to the effects of climate change, as climate change will spread the distribution of specific microhabitats and microclimates, such as nurse logs, canopy cover, and leaf litter. In this way, climate change acts as a catalyst and an amplifier for habitat fragmentation, loss, and stresses the availability of resources for organisms residing within the peninsula. So, for these last 8 or so slides, I'll be going through them at a constant rate to emulate a time lapse of the Hoh Glacier and the study area surrounding it in order to depict how land use has changed over time. Take note for NDVI how sparse vegetation, highlighted as orange, classified as orange, over time tends to fragment a barren ground, and how dense vegetation takes root in areas which already possess sparse vegetation. Same applies to NDSI. It's intriguing to watch how it fragments the terrain over time. So, as a whole, remote sensing is an invaluable tool to understanding how glaciers, in particular remote ones like the Hoh, respond to climate change. Through multispectral analysis, We can quantify changes in land cover over time and inquire why, and gain a fragment of insight into why a glacier, such as the Hoh, change over time and respond to outside forces like climate change. And now I will open the floor to queries. Thank you so much for attending this presentation, and I sincerely hope you have a wonderful day.